Hey everybody, today we're going to talk about molecular shapes. What shapes do molecules actually go into? The first thing we need to know is the Vesper theory. So what you need to do is pause the video so that you can write some stuff down. This stands, we call it the Vesper theory, the valence shell electron pair repulsion theory. So clearly the letters mean something. And you say, wow, what lots of words, but it's actually pretty easy. Valence shell electrons, you know what those are. Those are the ones that are furthest from the nucleus. And we care about them when they're in pairs, either when they're bonded to something or potentially when they're not bonded to something. And of course, electrons are all negative, so they all repel each other. So when you have pairs of electrons, they repel each other. That kind of makes sense. So that's what the valence shell electron pair repulsion theory is all about. Okay? And that's exactly what this stuff says down here, that in a small molecule, the pairs of valence electrons are arranged as far apart from each other as they possibly can be. So we have 5 basic shapes. Again, pause the video, write these down. They're linear, trigonal planar, tetrahedral, pyramidal, and bent. And you do need to know the bond angles. So make sure you write those down as well. Okay, so how do you determine shape? Well, when you look at your central atom, you count all the clouds on the central atom, and we're going to talk about what these clouds are. But groups of electrons are clouds. So, in other words, pairs of electrons. Now, the thing is they can be shared pairs, they can be unshared pairs, and in fact they can be multiple shared pairs. So they could be single, double, or even triple bonds, and they will count as one cloud. And based on the number of clouds, you can then determine the shape based on the Vesper theory. All right, so let's think about something where we have one cloud. Right? So here's an example of one. It makes one bond, it has a linear shape, and your angle here on this line is 180 degrees. So I have an example here. This would be, for example, chlorine bonded to chlorine, or fluorine bonded to fluorine. It's just two things, and they're connected by a straight line. So anything that you have where you only have two things, that's always going to be a straight line. All right, we have a video that shows the concept of having two clouds. So watch the video for me. All right. So here we have the central atom. The central atom is at the middle. It's that thing of duct tape right in the middle. And now we have two students who are pulling on the ends of the rope. And what angle do we have between the two students? Somebody tell me what angle we have. Is that 110, 120, 180? What angle do you see? 180. Okay, we're good. That's 180. So that's if we have a central atom and we have two things pulling against it. All right. So what you saw in the video was you saw one person over here, and you saw one person way on the other side, and you saw the central atom in the middle. Right? What you saw was a line essentially that went all the way across. So again, you see a 180-degree bond angle between these two bonds. Okay, so you can look at it this way, where the white thing that's in the middle, that's your central atom, and then the two red ones on the outside, those were the other things it was bonded to. Again, 180-degree bond angles. All right, well, here's a video when you get up to 3 clouds. So go ahead and watch this one. All right, so now we have one central atom, and we have 3 other atoms around that central atom. So now what has to happen is these 3 atoms need to get as far away from each other as they possibly can. The 3 other atoms need not pull back. Sarah, you need to move to your left. And Brian, I don't know if you can move to your right at all. All right, we're trying to get 120-degree bond angles here is what we're looking for. All right, so we were at 180, and that kind of sort of looks like about 120-degree bond angles with the different ropes, okay? So, guys, can you all pull one step forward with your ropes, please, so I can get all of you in that picture? Cool, that works. Thank you very much. All right, what you saw here was you saw one person way up here going to a central atom, and then you saw them going off in directions like this. And each one of these bond angles is 120 degrees. So again, the electrons, look at each one of these lines as a cloud of electrons. They're trying to get as far away from each other as they possibly can. The cloud of electrons is holding the central atom to each one of the ones that are on the outside. Okay. So if we look at this, here's another representation of it graphically. Trigonal planar shape, 120-degree bond angles. You need to know the name. Okay, this would be something like boron, which is in the middle. All right, what happens if you have 4 clouds? It gets a little bit more complicated, so go ahead and watch this video. All right, so now we have 4 people who are all attached to the center, and they have to get, you may have to go walk to the stairs, Brian, to manage to make this. You're trying to get 90-degree bond angles, okay? And that's actually what we do have. We have all 90 degrees, okay? Now, the problem is that if we look at, let's say, the 2 people who are, because people aren't going to know who you guys are, the people who are vertical in this, the one who has his back to you and the person who is directly across from him, all right, they're at 90-degree angles, okay? So if we look left to right, they're also at 90-degree angles, okay? Between any of the 2 people who are next to each other. But if we look across, they're at 180-degree bond angles. So what we have to do is start thinking in 3 dimensions. So we're going to work this up into 3 dimensions. So Brian, would you go to the top of the stairs, please? As in all the way to the top of the stairs. Oh, yes. All right. So now what happens is your bond angles change. All right, so now we have someone who is all the way at the top of the stairs, so that's actually pulling up. So if you look at those bond angles, they're not 90 degrees anymore. And so what they've done is they've all adjusted to be as far away from each other as they can. And these bond angles are now 109.5 degrees apart from each other. All right, when we first started out, what you saw something that looked like this, where these were 90 degrees. All right, but what we were trying to get at is from here all the way over to here, or from this one all the way over to that one, those are 180-degree bond angles. So in reality, we weren't as far away from each other as we possibly could get, because we were thinking in 2 dimensions. So when Brian went up to the 2nd floor, you saw that what we ended up with was this thing called a tetrahedral shape, where your central atom is in the middle, and then you've got 4 people out here on the outside, or 4 other atoms. Again, you've got 4 clouds. Each one of these lines is a cloud. And each angle that you see, it doesn't really matter which one you deal with. They are all 109.5 degrees bond angles. Okay? Now, this is true when you have the central atom is bonded to 4 different things and you have 4 clouds. So it's important that you have 4 clouds coming out of that central atom. If all 4 clouds are to other atoms, they're tetrahedral. But if you only have 3 clouds, they're going to be pyramidal, and if you only have 2, then you go to bent. So we'll talk about that in a little bit more detail right here. If you have 4 clouds, it looks like this. It's tetrahedral in shape. The central atom is in here in the middle. And then you have atoms all around the outside. Again, 109.5 degree bond angles. This is tetrahedral. But what happens if you only have 3 clouds? All right. I'm sorry, you still have 4 clouds, but they're only to 3 other atoms. Notice that the one up on top, I don't know if I can do this. Let's see what happens. Yeah, I can do that. That one that's up on top, it's not bonded to anything. So you'll notice when we drew it this way, we have an unshared pair of electrons sitting up the top. We have 3 shared pairs, that's these lines down here. All right. So when we look at that, we've gone from something that was tetrahedral in shape, here's something that's tetrahedral in shape, to all of a sudden going to something that's pyramidal. So what's really the difference? Well, frankly, guys, there isn't much. This is tetrahedral, and that makes sense. And when you think about each one of these bonds, each one of these, the electrons that are in here, these electrons, for example, that are in the middle, are being pulled up towards the chlorine, which is up here, and they're being pulled back down towards the carbon, which is here, if this was CCl4. So the electrons are being pulled in both directions. But if that disappears, then the electrons here are only being pulled down towards the carbon. And that's what you see here. The electrons are only being pulled down towards the carbon. And if they're pulled down towards the carbon, there's nothing pulling them back up, which means they're getting closer to the carbon, or they're getting closer, in this case, to nitrogen. And when they get closer to nitrogen, they're going to push in on these electrons just a little bit more. They're going to repel them just a little bit more because they're closer. So when that happens, these get closer. So instead of being at 109.5, they pull in just a little bit to 107. Well, what would happen if we lost another one? Well, if you lost another one, you'd go down to 4 clouds where you're only bonded to 2 other atoms. I have one of those around here somewhere, but I've lost it. So let's just go with this. Rebuild that one really quickly. All right, so what we have is we have something that looks like this, where we have a central atom. It has 4 clouds coming off of it, but 2 of them are going to atoms, and 2 of them are not going to anything. So these 2 that are not going to anything, the electrons are no longer being pulled out. They're only being pulled in towards the protons in the central atom. So they're going to come in a little bit more. So they're going to repel, they're going to repel these bottom guys even more to come in together. So your bond angle in here is going to be 105. So let me draw that on this diagram over here. Your bond angle here is only going to be 105 degrees, because these electrons, which are unshared, are pushing down and repelling these electron clouds even more. Okay, so let's actually draw some things and see what happens. If we have carbon, we have to think of how many bonds carbon makes, and what you need to do here is use your Lewis dot structure. Right? Remember that carbon has 4 valence electrons, and each of the hydrogens has 1. That's a total of 8 valence electrons. So we're going to put carbon, we're going to put carbon in the middle. We're going to put 4 hydrogens on the outside, because there are 4 hydrogens to worry about. Each one of those lines represents 2 electrons. So that's 2, 4, 6, 8. That's our total of 8 electrons already, so we're done. Remember, each hydrogen only takes 2. Carbon has 8 electrons all around it, so it's going to have 4 clouds. Because it has 4 clouds, we're going to have, to 4 different things, we're going to have a tetrahedral shape. So it will look something like this when we try and draw it in 3 dimensions. All right, so the Vespers theory says, well, what happens about nitrogen? Well, nitrogen has 5, and fluorine has 7, but there are 3 of them, so that's 21, so that's a total of 26. So when you draw this, you're going to say, well, nitrogen, fluorine, 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 out to here. All right, fluorine, fluorine. And what you're going to find out is each one of these has 2, 4, 6, 2, 4, 6, 2, 4, 6. You're going to have 2 that are stuck up there. So again, you have 4 clouds. You have 1 here with that line, 1 here with that line, 1 here with that line, and 1 here with this unshared pair. So we still have 4 clouds, but only 3 of them are bonded to something. So that means we're going to have a pyramidal shape here, where our bond angles are 107 degrees. We're going down to fluorine, 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 and up here we have 2 electrons. How about OF2? Well, again, we have 6. 7 times 2 is 14. That's 20. And when we do this, we're going to find out we have oxygen, fluorine, fluorine. That's 4, 6, 8, 10, 12, 14, 16, 18, 20. So again, oxygen has 4 clouds. 1 there, and 1 for each line. So that's 4 clouds, but only 2 of them are bonded to something. So we're going to end up with a bent shape, which is going to look like this. Same thing that water looks like. And here we're going to have a 105-degree bond angle in there. So try SO3. See if you can do that one on your own. All right, so we have sulfur in the middle, and we have 3 oxygens coming off of it. So we have oxygen, oxygen, oxygen. And we have that 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The problem is that sulfur is short too, so we're going to take 2 away from here and put them in there to make it a double bond. Okay, so how many clouds do you see? Well, here's 1 cloud. That's clear. Here's the second cloud. What about this guy? Well, remember we said that double bonds made a single cloud. So we only have 3 clouds here. So if we only have 3 clouds, that means we end up with something that looks like this, which is trigonal planar. Oxygen, oxygen, doubly bonded to another oxygen. These are all 120-degree bond angles. How about SO2? Again, see if you can do it. Okay, we have a total of 18 electrons. Sulfur clearly is in the middle. So we have 4, 6, 8, 10, 12, 14, 16, 4, 6, 8, 10, 12, 14, 16. That makes 18. So that means but sulfur right now only has 6 electrons. So we're going to get rid of those and put in a double bond there. So now this oxygen and this oxygen has 8. The sulfur has 8. That oxygen has 8. So how many do we have? Something's wrong here. We have 1 cloud. We have 2 clouds, and oops, right there, that was the one I was missing. We have 3 clouds. So we're going to have sulfur with that counting as a cloud, and an oxygen down here, and an oxygen down here. That's a double bond. Each one of these angles is, again, 120 degrees. All right, I2, really easy. Don't need to think about that one. Anything bonded to something else, if there are only 2 things, it's definitely linear, 180 degrees. No thought there. And how about our last one? Well, again, try and do this on your own, and then I'll do it for you. All right, we have a total of 10 valence electrons. Carbon clearly goes in the middle, and then we have nitrogen and we have hydrogen. Remember that hydrogen only takes 2 electrons, so we have a total of 4 so far. 4, 6, 8, 10. All right, well, carbon still needs electrons. It's only got 4, so we're going to get rid of those and put in a double bond. Now carbon has 6, so we're going to get rid of those, put in a double bond. So we end up with something that, in fact, is linear, or because we only have 2 clouds, one of them going over to hydrogen, and one of them going over to nitrogen. So it is linear. Okay? All right, that's it. So, in summary, we have the Vesper theory that you need to understand. You have to be able to count electron clouds. You have to be able to determine the shapes of simple molecules, and that's all we're going to give you guys, are these kinds of simple molecules. And you have to determine the bond angles based upon the Vesper theory. Now, there is a chart in your notes you may want to look at that will help you. But I've tried to go and give it to you based on the Vesper theory, so you don't need a chart, so you can actually logically reason through it. Okay? Thanks. Have a great day. See me if you have questions. I'll see you in class. Have a good one. Bye-bye.